Thanks, Bob. And good morning to everybody. I'm Chris Vorhees. I'm Vice President of Spacecraft Development at Planetary Resources. I'm honored to be able to talk to this group and be able to tell you a little bit about what we're doing. I don't do this very often and come out and give presentations. So every time I do, it's an opportunity for self-reflection and trying to put the story together. And I find myself kind of at a loss and needing to explain myself to a group like this because I've come and I'm speaking in front of the Mars Society for the first time. I spent 17 of my 19 years of my career doing Mars exploration and am now coming and ostensibly talking about something that doesn't have anything to do with Mars exploration. And for me, there's a very personal and professional and I think technical connection between what we're trying to do at Planetary Resources and what the objectives of this society are. And hopefully I can connect those dots for you today. If I don't, apologies in advance. But for some background, I'm a mechanical engineer in the space industry, which means I build the machines that help folks like Dr. Hassler do and discover the things that they do and make the findings possible. And I have to be one of the luckiest mechanical engineers in the space industry because my first job, almost 19 years ago, was while still in school on a little RC car shaped vehicle named Sojourner Truth. And I got the opportunity to ride a wave of a renaissance that I think has turned into a revolution in robotic Mars exploration, from designing and building and fabricating the little cleats on Sojourner's wheels, all the way up to leading the mechanical team that put Curiosity together and designed it. And so that's been a journey that I couldn't not talk about because it's a part of how I got to this. So I've gotten to experience, and no small part actually to the support of organizations like this, that revolution has occurred. I've got to see what it takes to get a vehicle that looks incredibly ugly at the start and not real clear what it really is or what it's supposed to do into something that looks like this, that packages all of those instruments that Dr. Hassler talked about, finding a good place for the RAD instrument to do its job, and also be able to move around, climb up a mountain, and make its own landing gear. And I do agree with Dr. Hassler. I was the one that came up with the Mini Cooper analogy, and in retrospect, the SUV is more appropriate. It is menacing, especially from this angle. It's my favorite. And then I've gotten the opportunity over the course of my career to have the pride and the abject fear of saying goodbye to the vehicle that you helped create and hoping everything goes well. I've also had the opportunity to embarrass myself along the way periodically in big ways and in small ways. This one is just always make sure you know where the mass properties of your vehicle is before you do the test. Just important. But you can recover, put together interesting equipment, operate it for the first time, make the best equivalent I can of footprints on the surface until we can put actual footprints. And then celebrate. I've had an opportunity to celebrate some incredible successes. For the record, I don't know how that flight spare hardware got onto the beach, but it was very useful. And I've had the opportunity to do amazing things and then live with the ramifications when they don't go so well. And I guess all of that The reason that I bring it up and I talk about it today is is that it shapes kind of who I am and how I approach problems, and it's actually kind of got me prepared for what ends up being the most challenging thing that I've had to do in my career, which is to stand up an organization from scratch and get Planetary Resources on its way to hopefully opening the frontier for space resources. So I'm not going to talk anymore really about Mars. If anybody does want to talk about it, I will talk your ear off about any of these subjects. Just find me after the session. So that seems like a tangent. Hopefully I'll connect the dots. There's lots of dots connected for me because I can't really do what I'm doing now without having done all of that. But I think there's a connection between asteroids and Mars, and hopefully I can convey that today. So why go after them, and why right now? We're still discovering asteroids every day, and we have really just started to learn about them in any detail at all. The exploration of these objects in space is nascent, but our interaction as a planet with them is intimate, as I think everybody in this audience would understand. The last and most direct example of that was the Chelyabinsk incident back in February that injured 1,000 people and could have been a lot worse, and we did not see it coming. But just as they are a danger, they are composed of incredible quantities of valuable in-space resources, some that are valuable just because they're valuable, and some that are valuable because they are in space. It's my belief, the belief of the company, and I think kind of a general consensus that humanity's sustained expansion beyond Earth is going to require resources, and I believe the asteroids are an enabling source of those. And I guess at our company, we believe that it's now possible to make accessibility of those resources commercially viable. And so that's kind of how I got into the mess that I'm in now. So just let's start with the first one. We're still discovering asteroids, and we're really just starting to learn about them. We've discovered about 600,000. The number changes all the time, so this is kind of a round number. Asteroids, both main belt and near-Earth asteroids to date, that is estimated to be somewhere between 2 or 3% of what actually exists in the solar system, so most of it we have not found yet. The total number of near-Earth asteroids, so asteroids that exist in the orbit between about 0.75 and 1.25 astronomical units. We've discovered about 10,000 of them, and we find about 3 on average new near-Earth asteroids every day. Of that set, 17% are energetically closer than a one-way trip to the surface of the moon. And if you consider the round trip to the moon and then back to the Earth, over half of those objects are energetically closer. To look at it a little bit of a different way, it's kind of hard to see in the light. This is how we look at it. I like to call this the dandruff plot of the solar system. And this is all of those near-Earth asteroids laid out over your opportunity to go and visit it over the course of the next decade. In delta V on the Y column. This is from 3 to 6 kilometers per second. 6 kilometers a second is what's needed to get from low Earth orbit to the moon. So these are objects, their time period, their relative size, that are energetically closer than the moon. And we take this kind of as our first set of targets. We cool it down. My God. Someone tell the owner that their subscription has expired. No. All right, let's hold for a second. Okay. So we take this list, we take this kind of this list and this graphical representation, we cull elements that have high orbital uncertainty, that have brightness characteristics that make it difficult to find, to things like synodic period. It only comes by every 50 years, so it's not really a useful target. Bring those down, and from that we create the candidate set of targets that we're interested in. So this is really hard to see, but it's a comparison between this and the next slide. This is where we were in 1997. In discovering asteroids, we discovered about 33,000 main belt and near-Earth asteroids. And it was just before this that we had watched comet Shoemaker-Levy 9 impact Jupiter. It was dramatic. It was exciting. I remember it happening. And then there was kind of a pause, and we thought, wow, that was a lot of energy. And there's a black hole on Jupiter that could swallow the Earth. I wonder what would happen if that happened to us. And that got everybody looking. It started the NEO office at JPL. It got Space Watch, the Catalina Sky Survey, and got people looking. And over time, we've taken that 330,000 number to 600,000. And the solar system now, for me, looks a lot different than it did when I was first starting my career. It's a crowded place, and there is a lot to discover, a lot to watch, and a lot to learn. We've also, over the course of the last 20, 25 years, visited just a handful. The first in 1991, it's 951 Gaspara, which is the first asteroid that we ever saw. It's a main belt that wasn't a point source of light in space. And and that was the Galileo spacecraft on its way to Jupiter. It also saw Ida, right here. And we found that asteroids can have moons. That's Dactyl, which orbited Ida, and that was the first binary asteroid that we discovered. It's actually a significant percentage of asteroids that have a binary. And so we've, just been able to visit a handful over the last 20 years from various spacecraft, from DI to Dawn, to Rosetta and Hayabusa. We have yet to find this, but just for frame of reference, that's the Death Star, 160 kilometers, of course, as everybody knows. Everything's to scale. Haven't found that one yet. The one that I want to talk about a little bit more, you can't even see on the chart. It's Akala, which the Hayabusa spacecraft visited, and it's kind of the one that's in the sweet spot of size, and it's less than a kilometer in diameter, although diameter is kind of the wrong way to look at it. It's more of a potato. And the interesting thing about Akala, besides that its size is relevant, is that before we saw Akala, and it was just a point source of light in space, there were even odds, in fact a majority opinion, that this could be nothing more than a giant homogeneous singular rock in space, and that there was no way that with the minuscule gravitational influence that a rubble pile could actually exist. And you can very clearly see that that's not the case. It's a rubble pile at any scale that you look at. There's enough influence between the gravity, van der Waals forces, and the spin rate of the asteroid to not only collect little bits and pieces, some sized the size of a car, some just grains, and you can see that grains have actually sorted to the top and to the bottom of the object, and this was not even thought possible before actually visiting, which for me is the best reason to go. When people talk about how you're going to mine asteroids, it's like, well, the first thing you need to do, just like you do on Earth, is to understand your ore body. This is an ore body in space, and you mine it differently if it looks like that than if it's a giant hunk of something. So, asteroids, just to get to my second point, are composed of valuable in-space resources. How do we know this? Well, it turns out, it's kind of two ways. It turns out the Earth is an incredibly good sample acquisition device for asteroids, for lack of a better way of saying it. We collect about 100 tons of material on average each day. Some of it makes it to the ground in the form of meteorites. A lot of it doesn't. And the interaction with the Earth's atmosphere changes the composition and the chemical signature of these meteorites. So they're not really native for what they are out in space. But they're pretty good indications in a lot of cases of what we would find floating around. And from that, types, three basic types, a stony type, carbonaceous type, and a metallic type have kind of come into being, and lots of subtypes and even more subtypes as the science has matured. We've also done a lot of point source observing. This is how we detect it. You take pictures, you take triplets, you find the moving objects in space, and you find that asteroid. There are other things you can do besides detection. With photometry and just looking at the relative brightness, you can tell its spin rate. You can get a rough idea of its size, but not really, because you don't really know what it's made of. So you're making an assumption about albedo, which is kind of one of the reasons that we want to go out and visit. And you can also do spectrophotometry, and you can get some information about the composition of elements simply because of the light that it reflects. We've been able, though, to do a ground truth of that measurement, just as Dr. Hassler talked about. Ground truthing is critical. We've done ground truthing of that exactly once, back, I think, about 4.5 years ago, with an event and a meteorite impact that happened in North Africa that we found 2 weeks before impact. And there were a series of observations like this of photometry and spectrophotometry in space, and then a collection of the material after it after it impacted. Yeah, that's the only time that we've been able to do that, and that's really probably step one of Planetary Resources mission, is to do more of those. So what's there? First and foremost, in carbonaceous asteroids, there are volatiles, the most interesting of which is water. We just talked about water as a good radiation shield. It's good for lots of things. It's an industrial solvent. It's life-sustaining, and it's fuel, both in its raw form in space as well as in its separated form. Other chondrites exhibit metallic chondrites, or a metallic fraction chondrite, I should say, exhibit significantly higher quantities of things like rhodium and palladium and osmium and platinum that are sometimes hundreds of times in composition and in density of that composition than the richest mines that we find on Earth. Interestingly enough, some of the richest mines we have on Earth are sites of previous asteroid impacts. The one that comes to mind right now is the Sudbury Basin in Ontario. It is one of the richest nickel mines in the world. It is an asteroid impact, and that's where that came from. And finally, in that case, the metallics, for me, while the water is kind of the most critical, the metallics are the most fascinating. There are objects that are 90% iron floating around in space in crystalline structures that can only form in the presence of microgravity, and in purities that rival the refined product that we get out of the best processes we have on Earth. So that's what's floating about our head. For me, in getting into this subject matter, it was the magnitude of the material that was interesting. and kind of the aha moment. One 75-meter carbonaceous near-Earth asteroid has enough H2 and O2 to have filled 135 external tanks. And that's kind of a big deal. One 500-meter LL chondrite, which is the platinum-rich variation, has more platinum than is mined in all of human history, which, for frame of reference, is probably like three-quarters of this stage, and then about the same, about 6 meters high. That's the amount of platinum that we've been able to extract with much expense and much effort from the crust of the Earth. So those are like, those were aha numbers for me. And I think that's what drives the desire to go out and see what's there. What's interesting for me is that those materials not necessarily are interesting to bring back to Earth, although there are uses for it. The most interesting one for me is using those resources in space to further space exploration. And I just pose a what if. So here's that space shuttle again. To launch into low Earth orbit, we use several 100,000 kilos of LOX and liquid hydrogen. And that actually doesn't do the trick. We needed 2 SRBs to get it off the ground and give it some oomph. And with that, we get to 350, 500 kilometers of altitude. For me, this is an illustration, and it's hard to describe to folks outside of a community like this of just how hard it is to leave the planet at all. And we spend almost all of our energy and our effort just to do that. So what if we refueled and on orbit? We just took that external tank and fueled it up again. That's somewhere between 7 and 8 kilometers a second of delta V just to get off the gravity well. And well, you can do lots of things. And I thought of different ways to say it, but Robert Heinlein said it best. It's not completely technically accurate, but it's close enough. You have access, and access makes all the difference. You have access where you want access, which is in space. And I think part of our problem here is that we tend to look at space as a distance thing, and people describe to it, and it's like Mars is 250 million kilometers away, and or you had to travel 250 million kilometers to get there, and it's a really long trip, and it's kind of the wrong way to look at the problem. And the problem is not distance, it's energy. And terrestrially, distance and energy are the same. And if we have to go further, we have to expend more energy. But it's not actually the case in space. We spend all of our energy getting off the ground, and if we could find a source of it in space that was useful, especially as high octane as hydrogen and oxygen, well, wouldn't that be something? So this is definitely a chart that's created by a business development person. And the first time that I saw it, I'm like, wow, this is really incredibly optimistic, and I'll never use this chart in a presentation that I give, because I'm an engineer and I don't believe these kind of massive radical projections, because that kind of stuff never happens. And then he showed me this one, and I thought, okay, that's interesting. And the one on the left is the progression of aviation fuel for non-military usage over the course, well, of the last century. And the point was, maybe it's not so crazy to expect logarithmic change in resource if the time is right and the usage is needed. So the reason that I'm involved in this is that we think it's now possible to make accessing the resources commercially viable. And we think that because tools to design vehicles and tools to do useful things in space have progressed just an unbelievable amount. And even in the last decade, the types of things an individual engineer was able to do at the beginning in 2003 of MSL were significantly different and significantly lower than the same engineers and their output in 2010 when the vehicle was being completed. We think being able to move away from the government space and take access to those tools and take a different risk posture may actually open up interesting things. And we use as inspiration some of my friends and collaborators at Scale Composites that were able to, with a team of about 30 people and some support from a Mr. Paul Allen, were able to do what it took the entire thrust of the U.S. Air Force 50 years previous with Alan Shepard, and we're able to accomplish that in a radically different way for radically different reasons. We think we can do the same, just with robotic spacecraft. So Planetary Resources was founded with a mission and vision to go out, identify interesting targets, prospect them, and then mine them, and bring that resource, those resources, back to bear to a point of need, whether it's in space or back here on Earth. And I guess it started and it's founded with a belief that it's only in pursuit of those resources that we will be able to make a sustained foothold outside of Earth orbit and that frustrating trap that we appear to be in. And really the final one is to diversify humanity's resource base. We have one right now. It's getting increasingly expensive, complex, both technically and socioeconomically, to go after those resources. And it's not really nice to have all of our eggs, our resource eggs, and humanity's eggs all in one basket. So that's kind of an audacious goal. It's going to take a while. What are we going to do right now? Right now, we're trying to figure out the best way to go out, prospect, and establish rights for usage for the most valuable near-Earth asteroids. As Bob mentioned earlier, we were able to get this off the ground because some folks helped us and helped us at the right time. Some because they were interested in the technical problem, some because they were interested in the legal and policy problem, and some that just wanted to see it happen. And that's what's gotten us going. The company was founded by Peter Diamandis of the X Prize Foundation and Eric Anderson of Space Adventures. They hired president of the company. His name is Chris Lewicki. Chris Lewicki is a fellow compatriot of JPL and a flight director and mission manager for both the Mars exploration rovers as well as the Phoenix program. He found me. We found others, both from inside the aerospace industry and most specifically from outside of the aerospace industry. And we find inspiration both within how problems are solved in the automotive industry, as well as how they're solved in microelectronics, industry microelectronics, industrial microelectronics, and commercial. So, how do you go about doing this? So I thought I'd put my principles down. You need to own the system so you can own the system risk and balance it appropriately. When it's quantized and you don't own all the pieces, it's difficult to do that. That requires you to vertically integrate, and you also need to do that in order to be able to mass produce, which is our plan. It's not really helpful to mass produce complex spacecraft, so you need to make them as simple as you can, you need to make them as general purpose as you can, and you need to have safety in numbers instead of in polishing the risk out of the problem. Designing the system to be acceptant of advances in technology. This one seems kind of like a no-brainer, but it's one of the hardest things for the aerospace industry to do, and we're finding our way through that problem. We also want to take incremental technical baby steps and use Earth orbit first as our test bed, and then as an operational platform, and then as kind of a jumping off point. And we want to take asteroid prospecting costs and turn them into their terrestrial equivalent, and look at asteroid prospecting kind of as the resource industry looks at preliminary explorative analysis, which is the first step in the process. So for us, what are we doing? Why are we doing it? So next year, we're in the process of building a set of spacecraft. Oh, I should say, our spacecraft are called Arkid. That's the name of our spacecraft. It's yet another homage to the Star Wars universe that was slightly altered so that we didn't get sued. But it's an homage because we got a lot of respect for Star Wars, and anyway, won't go into it too much. But we've created a vehicle we call Arkid 3. We're building them now, and I say them because we build and do safety in numbers. Like to build lots of spacecraft and not just one pristine, perfect object. Mostly because I was responsible for one pristine, perfect object in MSL, and that gets pretty scary. That's to take a lot of that vertically integrated in-house core hardware and software and find out if it works, find out what works, what doesn't, change it, try it again, and use orbit as a test bed. Next step is A100, and it represents the core spacecraft technology. It represents the spacecraft we want to have at the asteroid, just not at the asteroid. So we practice proximity operations, and we can also use it for interesting things while it's in orbit. And the most interesting one, I think, for us is not necessarily asteroid detection, but follow-on characterization. It's an instrument that is dedicated. It's an instrument that is available 24 hours. It's an instrument that's above the Earth's atmosphere, and we can do long stares, bring orbital uncertainty down, get spectral characteristics, and get photometric measurements. And because most of the objects, most of those 600,000, we know where it is, kind of. But we've looked at it just long enough to make sure that it's not going to come around and kill us. And then we kind of lost interest, because that's really the focus right now. So we need to do better than that. And then we're using this platform as an element of our public outreach that we call the Arkid Space Telescope, which you may or may not have heard about. Next step is A200. A200 adds optical communication and propulsion to A100. We start in GTO and GO, and we kind of move out. And this is kind of our first foray into interplanetary space and asteroid flyby. Maybe not rendezvous, but flyby would be our first set of targets. And then we end up with A300. See, four easy steps. And in A300, we send multiple spacecraft for evaluating, doing that preliminary explorative analysis, evaluating the target, establishing rights for usage, and then doing in situ activities that help us with those next steps. And then we continue to engage NASA. NASA has its own asteroid interests, and we continue to be involved to the level that we think is appropriate and the level that we think is beneficial to both groups. And we want to engage the public as we go, and we are constantly looking for ways to do that. And so after this, the thing that everybody asks about, the mining, this is all the easy stuff before the real work starts. But it's establishing that you can do it, that you can reach it, that you can do it cost effectively, and that there's something there that's of interest, and that you can bring a market to bear. So it's kind of after all of this that the really interesting part happens, and the really hard work starts. So just to conclude, I ask myself this a lot, so I figured I'd put it on a slide. So it's going to take a long time. I've left my great career in Mars exploration, and I'm going to dedicate the rest of my career to making this happen. And I could just be pushing on a rope the whole time. You know, it's a really hard thing to do, to first leave the gravity well and then do something useful. So why try? So I lied. I'll go back to Mars one more time, because sometimes it works. Sometimes you're asked to do audacious things. In this case, I was asked by my principal investigator to perch a vehicle right at its static stability limit and do some exploring on the lip of Endurance Crater. And I didn't think that that would be possible, and it turns out you should just push those systems to the bleeding edge, because you can take pictures like this. You can change the way you view yourself and the universe around you. And I'm bolstered because support comes from all corners. I mentioned the Arctic Space Telescope earlier. That's kind of an experiment for us in engaging with the public, because we run a lot of experiments, some technical and some with the company. And the outcome of this experiment, the purpose of this experiment was to say, are people interested in being directly involved in a mission? Not just passively, but actively. And we didn't really know. So this was a way to find out. So now I have 18,000 co-investigators for my spacecraft. And I really can't wait to see what they do with the machine, because they'll think of ways to use it that I have not. And then we're providing our data and a pipeline to the public through a collaboration with the Zooniverse, which you guys may know from Galaxy Zoo. We're developing Asteroid Zoo, which is going to take data from our pipeline, data from the Catalina Sky Survey, and 20 years of previous data, 16 terabytes, and hand it over to the public and see what we can find, because we haven't found all the objects that are even in the data that we've got already. And Catalina believes they were 50% successful. So there are even more to discover in the data that we've already acquired. So that inspires me to keep moving and try to move one rung up the ladder for making space more accessible for all of us. So with that, thanks to the Society for the opportunity to talk, and thank you for listening.
Question. What does the Outer Space Treaty say about your ability to claim an asteroid or a part of an asteroid?
It says that no sovereign nation can claim can claim the moon or a celestial body. The jury is still out on rights for usage, and it's a subject for which the law is at its frontier. And we look to terrestrial analogs for how property rights and mineral rights and rights for usage and the laws of the sea and how we handle resources on space, or resources on Earth terrestrially. And honestly, that the legal path is just as interesting as the technical path. We have another group that I haven't talked about here that's just working the legal and policy issues associated with being able to do this. If you don't work those in parallel, then you end up with one part of the problem not solved. Part of what the spacecraft will technically have to do will likely be influenced by that legal and policy. So for me, that's fascinating as an engineer that's been driven mostly by scientific investigations to be driven by a different purpose using the same platform.
I find it interesting that you compared your business plan with the history of air transport, and I wondered if that was an accident or on purpose, given the fact that in air transport, there have been so many bankruptcies and so many financial struggles.
I guess it wasn't an accident. I still think it's an interesting and relevant analogy for where we currently are with space transport, which I would say is if you're flying from Denver to New York and you're relocating for 3 months, you have to take your luggage and all of your food and everything that you need to survive, you have to take on that plane. And then when you get to New York City, you unload all of that equipment and you destroy everything but the cockpit of the aircraft. I mean, that's how we explore space right now, and that's kind of akin to the one-offs that the Wright brothers had back in the early 1900s. I think you would not argue that our use of aviation commercially is much more substantial now than it was then. It's been incredibly volatile, and it's matured, it's morphed, it's changed. The real thing is, and the real question, I think, and it'll be a question until we find out if there's a market in space, is can we incite, is the existence of a resource in a space, isn't it enough to excite the usage of that resource for transportation, not on the Earth, but off of it? And for me, that's the interesting question.
When you reach the last stage and you begin exploitation of the asteroids you've chosen, do you expect to mine them in place or capture them and bring them into orbit closer to Earth or the Moon to exploit them here?
I would say that is to be determined and target specific. I'll give you my opinion. I like refining in place, but I'm a robot guy, and I believe I can do anything with machines. So that might be a bias. I like returning the product from the source to the point of need. But I think the jury is still out for us. And a lot of it has to do with not knowing exactly what we're going after. I think once you see your target, and you're not talking about it in generalities, but you're talking about it in a specific object, your opinion may change. Mine may change.
Thank you, Chris. I really admire what Planetary Resources is doing for the innovation and pioneering paradigm that you're setting up. So my question is, in your plan for the asteroid mining, are you going to be using robotic miners or astronaut human miners, or a bit of both?
Well, I think it's pioneered robotically. Kind of just to go back to the way I answered the question, I guess that's my bias, because I think that's where we'll start. I don't know that that's where we'll end up, and I don't know that it would be appropriate for me to predict where we end up. For me, there's an event horizon in all of this that occurs after you have acquired a sufficient amount of information about the targets that are of most interest. You've established value and you've established market. At that point, I actually can't see myself. I would not want to project beyond that because I don't really know what happens. But that all has to set the stage for what occurs next.
All right, I think we'll
I feel
have
like
to
that
end
was
it
a
there.
deeply dissatisfying answer, so I apologize. But it's kind of the truth.
All right, thank you, Chris.